So now I think we are done with the minus part. Okay, so we have claimed that the polar operations on the channel W, they do something to the Bhattacharya parameter. So I owe you the ZW plus. This is actually even easier. So Z of the W plus, I'm supposed to go over all the outputs of the W plus. Remember, the outputs of W plus are Y1, Y2, and U1. So it's a summation, which is a triple summation here. Okay. I'm supposed to put here the W plus of Y1, Y2, U1, given that the U2 is 0, and the W plus of Y1, Y2, U1, given that the U2 is 1. Okay. We know what these things are. We know how to write these W pluses in terms of W itself. If the U2 is 0, what we get is that the first channel gets U1, the second channel gets 0, but with a 1/2, because remember that the W plus of something something is always 1/2 times W of Y given something, and W of Y2 given U2. Okay. And this guy is also 1/2 W of Y1 given the opposite of U1, because the first channel, X1, is the summations of U1 plus U2. If U2 is 1, X1 is exactly U1 complement. And then we have here W of Y2 given 1. The U2 is being fed directly to the channel 2, which creates Y2. Okay. So this one, again, I can group the terms together. First of all, these halves, they come out. I have 1/2 here. Okay. And then I can put a summation over U1, summation over Y1. And I have here the square root of W of Y1 given U1, the opposite of U1. I've accounted for this term and this term. What is left is the summation over Y2 Y2 given 1. Everything is here at this moment, right? Okay, good. So now we're in good shape because of the following. This is exactly equal to ZW. We are going all outputs of W indexed by the variable Y2. The output given 0 and output given 1, product square root. That's exactly the definition of ZW. So that thing comes out. You can push, it's a constant, it can come all the way up here. Okay. And then this summation over here is also the same. Regardless of the value of U1, you're going over all outputs of the channel W. And if U1 is 0, here is the square root of Y1, the output given 0, output given 1. Or the product is done in the exchanging the multiplicants. But multiplication is, what do you call this? Commutative, right? So whether you multiply A times B or B times, it's the same thing. So this is also the W for every U. So summing, what you're doing is you're summing over all U1s. There's only two values, 0 and 1, of Z squared. Okay. So you get 2Z squared in this whole sum. You divide by 2, you get Z squared. So we see that the going in the plus direction simply squares the Bhattacharya parameter Z. Okay, fine. So now that we have this lemma, I should say a few more words. Let me draw here one more figure, which I kept drawing all the time. Let me draw it once more. I'll start with the channel W. And there are two channels we create from this W, okay, which is the W plus and the channel W minus. From this, we also create the channels W plus plus, plus minus, goes on like this, right? So what we did previously when we did our computations about showing polarization does happen, what we're doing is the following. This is essentially a tree of channels. Okay. To each channel, I can compute, for example, its I. So I can slap a I parentheses around each of these things. And on the columns, I was computing various statistics. I was computing the average of the i's, the average of the squares of i's, etc. I can do the same thing with the z's if I wanted to, and so on. Right? We could do all sorts of things here. Okay. I can also do the following thing. For example, computing the average of the i's which are here is the same as I pick randomly a point in here. Okay. So then the value I get, the I of the randomly chosen channel in this column, is going to be a random variable. And the expectation of this random variable is exactly the mu that we computed for this column. The second moment of this random variable will be exactly mu I was computing in here. Okay. All right. So let me actually create these random variables by climbing this tree randomly. What I'll do is the following. I'll start at the root of this tree, okay, and I'll flip a coin, fair. The coin is going to come out to be plus or minus. If it comes out plus, I'll go in the up direction. If it comes minus, I'll go in the down direction. Okay, so tree is sideways, sorry. And then I flip one more coin. If it is down, then maybe the next coin comes out to be plus, independently chosen. Okay. Next coin comes, let's say, minus, independently chosen. Okay. The thing is, after 3 coin flips, I'm going to find myself in one of these 8 places, chosen all with equal probability, 1/8. So I can think of myself as my previous computations. I can think of as computing the, so that these plus minus choices be indexed by, let's say, I don't know, S. Okay. So the S1, IID random variables with probability that each SI is equal to plus is equal to half, and the probability that the S1 is equal to minus is equal to half. You do each of these things have the same distribution, independent of each other, and then this W S1 up to SI is a randomly picked channel at the ith depth. Okay? So, for example, if I take a look at this, this is now a random variable. Okay? It can take on 2 to the I possible values, I of the W plus 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 up to I of the value, I of the channel W minus minus minus, each equally chosen. So expectation of this is exactly what we were previously calling mu I. The expectation of the square of this same thing is what we were calling mu I, and so forth. Okay. All right. So, and in fact, let me actually define these things. Okay. So this, in this thing, the I of the W S1 up to SI is a random variable. Let me give this thing a name. Let me call this thing I sub small I. Okay. So the I0 is a constant. I0 is with probability 1 equal to the I of W. Okay. There's no plus or minus signs on it. I0 is a constant. I1 takes on 2 possible values, I of W plus or W minus, and so forth. Okay. Similarly, I could have defined, let's say, Zi to be the Z parameter of the same thing. There's also a random variable like that. Okay. Good. So now, what we showed before was the following thing. What we previously showed was the probability we showed previously by simply saying that since the fraction of channels at level I, or at column I, which are moderate, goes to 0, what we showed was the probability that the I sub I, being in the interval delta to 1 minus delta, the limit as I goes to infinity, this is 0. So this probability is exactly the fraction of channels. This quantity is exactly equal to the gamma I of delta that we had defined before, because it's counting the same thing in the most obvious way. Since the probability distribution is uniformly distributed on the ith column on 2 to the I things, computing probability and computing fractions are exactly the same thing. So now, you might be wondering at this point, okay, since we are doing the same things as we had done before, why am I introducing this strange complication of these climbing this tree randomly, making random variables out of things which we already computed before as being actual numbers and so forth? There's the following reason for that. You can view, previously, we looked at each column individually in isolation. We computed statistics on the ith column, computed statistics I plus first column, without taking a look at how are the ith column and I plus first columns now correlated. Because now what you see is that if you find yourself at the ith moment I sub I is this, then at the I sub I plus 1 can only take on 2 values. It cannot take on everything here. So there is a structure in these I processes. There's a very nice following structure. It has the following thing. Observe that if you take a look at the expectation of I plus 1, so what can the value of the I plus 1 be? Given that I tell you everything which happened in the past, I give you the I0, which is equal to I of W, I1 up to all the way to I sub I. So I tell you essentially by giving these things which path I have taken up to level I. I tell you that I have followed this particular path. You can discover what the path is by checking if I1 is more than I0, you must have gone above. If I2 is less than I1, you must have gone below. So you know which path you have taken. So I told you where exactly on this tree you are after doing this I steps of these plus or minus things. At that moment, you know exactly what this value is. And now there's only 2 possible values of the I of I plus 1. It's either the plus version of the channel that you stuck at, I of that, or the minus version of the channel at the ith level. Okay so far? All right. But these 2 things, these 2 channels that you can create, the plus and the minus versions of the channel that you are at the ith level, its average value is exactly the I of the channel that you started from. So it's exactly equal to I sub I. Okay? So it's a process. It is sort of like a fair random walk. Okay? If you think of this as being a game of chance, okay? And if you think of this capital I as being your fortune at time I, so you have somehow arrived at a fortune at time I, and you play the game one more time, the expected value of your fortune after the gambling is still the same as what you started from. So the casino is not cheating you, nor is the casino giving you some extra advantage. Okay? So this is a fair casino game. Now such processes have a name. The processes for which given everything happened in the past, if the expectation of the next step is equal to where you currently are at, such processes are called martingale processes. Okay? This is called a martingale. Martingales are a very well-studied topic in probability theory because, for example, all nice random walks, they can be converted into martingales, and people know lots of properties of martingales. One interesting property, maybe the main martingale theorem, is that bounded martingales converge. Okay? So let me say this thing in more proper words. So this I has a value between 0 and 1. So boundedness we already have. Okay? So if you think of what's going to happen, so a realization of this process is you follow some path along this tree, okay, and you'll encounter a sequence of I values. Okay? You'll encounter this I followed by the I which corresponds to this, and maybe that one, maybe this one, etc. Okay? So you make one experiment, you flip your coin, you give the monkey a coin, he flips the coins, we'll trace a path in this tree, and we'll encounter a whole sequence of numbers. Now these sequence of numbers, it might be a converging sequence of numbers, or it might be a non-converging sequence of numbers. There are only 2 possibilities. Okay? And I ask you the following question. What is the probability that when this monkey flipped these coins, will encounter a path for which the sequence of numbers that we encounter is a convergent sequence? Okay? All right? So this could have been any probability a priori, But knowing that it's a bounded martingale, this probability is 1. Okay? No matter how not no matter how, but with overwhelming probability, these coin flips that you're going to encounter, that you're going to choose, these S's, which will take you through this path, you will encounter a convergent sequence of I's. Okay? So there is 0 probability that the sequence that you encounter is going to be oscillating between anywhere and anywhere else. Okay? So martingales have this convergence property. It's an important one. Okay? So that was actually how the original proof of the polarization theorem was given. Because since this is convergent, okay, you would then, so such martingales, so together with, we have this also, this and this together, these two things imply that the I sub I converges with probability 1. Okay. Consequently, the difference between I plus 1 minus AI goes to 0 almost surely with probability equal to 1. So no matter how these, not no matter how, with overwhelming probability, the coin flips are such that this thing happens. But then what we saw was the following thing. The difference between these things is greater than, so whenever, okay, I should say the following. We also know that I of I is between delta and 1 minus delta implies at the next level you create either the plus or the minus channel whose difference between the channel that you have is at least kappa of delta. We know that. Okay. So if this is going to 0, okay, this cannot be happening. Okay. So the probability that the I sub I between delta and 1 minus delta has to go to 0, because if it did not, then this event will be happening with probability something, but that event cannot be happening because you're supposed to go to 0. Okay? So consequently, this probability must be going to 0, which is what we had shown by this more elementary argument by looking at the second moment of these I's. But this gives the original proof of Arakan went through this argument. Now this is going to be important for us when we analyze the process Z. I'm not doing this thing just because I want to show you the historical proofs of the polarization. I show it because we need this. Okay. Now, unfortunately, of course, in this proof, for those people who have never encountered martingales before, I simply pulled out a rabbit out of my hat saying, martingales converge. Boom. Okay. So if you ask me to prove to you the martingale convergence theorem, I could do that, but it'll take me a bit more time. Okay, so this is something that is taught in probability theory classes. It's one of the important theorems in this business, so it will take a while to establish. It's actually a very nice proof, but I don't want to spend time. It's better spent taken from a true mathematician rather than like me, who pretends to be sometimes. Okay, so this probability, as I goes to small I goes to infinity, this thing goes to 0. Okay. But now that we know this, that this sequence of monkey climbing this tree will encounter a path for which I of I converges, and indeed this I sub I converges only to two possible values, either to 0 or to 1, because of this one. Okay? So if you converge, you know for sure that you converge to 0 or to 1. So there are only two, well, there are three kinds of paths. Okay? The first kinds of paths, they make the I converge to 0. The second kinds of paths, they make the I converge to 1. And the third kinds of paths, that the I converges someplace, actually no, I cannot go anywhere else, I does not converge. Okay. This third kind of paths, they have collectively 0 probability. Okay. So the total probability of these third kinds of paths is 0, okay, because I converges with probability 1. And then the ones who converge to 0, those paths have probability 1 minus the I of the original channel W. And the probability of the paths which converge to 1, they have total probability, the I of the original W. If this had mutual information 0.7, 70% of these paths, with probability 0.7, you encounter a path for which this I process converges to 1. With 30% probability, you encounter a path for which the I converges 0, and with 0 probability, you encounter a path for which I does not converge. Yes? Yes, martingale comment is another way of proving this thing without doing any of this second moment computations that we did in the morning. So no kappas, no anything. Well, the kappa is still here, but so here's the deal. There's a difference between. So what we did earlier was to show only this one, to show that the this i's, they're always closer to the ends. Okay. Now, a convergence theorem such as this, a convergence statement such as I, does not make statements about individual subindices, which we're making it here. Okay. It makes a statement about all the subindices in totality. Okay. So to give an example, maybe it's this. Think of the following sequence of random variables. Okay, I have random variables, let's say xi, I from 1 dot dot, etc. And the xi takes on only values 0 or 1. It takes the value 1 with probability 1 over I. Okay. It takes the value 0 with remaining probability. Now with the following statement, the probability xi is equal to 0 as limit as I goes to infinity is 1. Okay? So the xi's are each xi, well, for large I, xi happens to be equal to 0. Okay? But if I ask the following statement, what is the probability? And suppose the xi's are independent. So these are independently chosen. Okay? So now, if I ask the statement, will the limit of xi exist and will be equal to 0? You would ask me the following question. For limit of xi to be 0, there has to come a point, say n. From that n onwards, you should always encounter zeros and never a 1. Okay. But that event has 0 probability. Okay, the probability that if I give you the n, suppose 1,000,000, and I ask you the probability that after this 1,000,000, everything that you choose is going to be all 0, has 0 probability because the summation of 1 over I diverges. You're going to encounter the expected number of 1s that you encounter from some point on is still infinity. You're going to encounter, no matter where you start from, no matter how deep an I that you choose, there's still going to see an infinite number of 1s because the summation of 1 over I from wherever you start this I from, if you go to infinity, is infinity. Consequently, you can never guarantee for me that I'm never going to see a 1 again. Okay. So this probability of this is 0. Even though each xi is highly likely to be, for large I, each xi is likely to be 0, the chance that xi will get to 0 and stay there, okay, and never jump up to 1 again, it never happens. Okay, so there's a difference between convergence to 0 and probability of something equal to 0 being high is not the same thing. Okay, because here we're talking about simultaneously the tail of the whole process at the same time. Okay. That's the difference between, for example, things like the strong law of large numbers versus the weak law of large numbers. So these kinds of statements are for the strong law. These kinds of statements are like the weak law, okay? Analogs of these things. These are none of these things are the strong or the weak law, but they're analogs of this statement. Okay. This was a diversion, by the way. So this has, in a sense, little to do with the thing, but it was good that it's asked because I will use it for the z. So now what we have known is the following thing. So we have seen the limit of I sub I is equal to 1. This has probability IW. Okay, so 70% in the running example that we had. With 70% probability, you'll encounter a sequence which converges to 1. Yeah. Yes, sir.
We are talking about the symmetric random walk, right?
Symmetric random walk on this graph, yes.
So if we somehow skew the properties towards more W plus,
yes,
we can ensure that the fraction of channels which have a higher capacity than the original channel increases much more as compared to, right now we have the fraction is I of W.
Yes.
But then maybe if we could somehow skew this random walk, we could achieve a much better.
Very nice question. So what you're suggesting is the following thing. Let us skew the probability distribution to give more weight to the channels which have more plus signs in them, for example. Now the problem with this is that, yes, you can do this, But the point is that at the end of the day, I need to know the number of these channels, because the rate, communication rate I'll be measuring is that how many channels did I use, how many of these U's I'm sending, divided by the total number of channel uses I made. So at the end of the day, I have to bring this thing down into what fraction of the channels counted by each channel given the equal weight 1 over 2 to the I is good. Okay? So because of this, I am stuck with this fair random walk. Okay? If I could skew things around, I could, for example, skew it with probability 1 here, and I'll end up with probability 1, I'll go to, I'll find a perfect channel. Unfortunately, doing that computation does not help me to figure out what is the, among these channels, how many of them are good, because that's the number I need in actually when I'm doing the coding, because I'm going to choose among these capital N of these U's, some of them are going to carry data, okay, and I need to know the number of them. Okay, so if out of this N, 50% of them are carrying data, I'm communicating at rate half. Okay, because of this, I need to know the number of these U's. And if I weigh these channels different probabilities and compute the goodness with that, then I'm weighing each of these channels with different numbers. I cannot get the count of the number of channels that I need. Okay. So now we have these things. In the light of what we showed with the relationship between the Z and the I, okay, of course, then this is the same as if the I's are getting close to 1, Z's are getting close to 0, and vice versa. And the same here is that if I's are getting close to 0, the Z parameters are getting close to 1. So this is the same as the probability that the limit over I, Zi is equal to 0. This is the probability that the limit over I, Zi is equal to 1. So as the I process is going here and there, the Z process is doing exactly the opposite, but we know where the Z converges to, okay? Because we know that I converges to 0 or 1 with this mass and this mass. Z converges opposite numbers with exactly the same masses as the I did. Okay? All right. Because Z process itself is not a martingale. Okay? Okay? It says, it in fact is something called a super martingale, because we haven't shown this thing in our proof, but if I had done a slightly more involved computation, we could have shown that the Z of W minus is approximated not just by 2Z, but is 2Z minus Z squared. Okay? Which will then make the average of the next Z's to be less than the current Z that you start from. So the Z process has a propensity to go towards the 0. Okay? Okay. All right. So it is not a martingale, it is a super martingale. It wants to be closer to 0 than where it is. So now, let us take a path for which this happens. So what I want to show is the following thing. These are the good channels. These paths for which the IW is getting close to 1, or the ZW getting close to 0, are precisely channels on which I'm going to in fact do coding. Okay? I want to show that on these channels, the Z is really small. So to be able to get a good estimate on the probability of error of the code that we are going to create. In fact, I remarked to some of you earlier, after the class, of the following thing. Because somebody was worried about error propagation. Who was worried about this, actually? Oh, you were. Okay. The very legitimate concern, because you see, we make these decisions, okay, on these U's. We make these U hats. If we make one wrong decision, we'll probably mess up all the following decisions too. Okay? So we said this, that the equivalence between the Gini helped and unhelped decoders is true only if we consider the block error probability. Okay? So what I had to show you is the following thing. We had these channels, WS. We have these 2 to the I channels at some moment. Okay? I'm going to find a subset of them which I label to be good. Okay? So among these things, we have this collection. We'll go to a sub-collection of, let's say the good channels. This is going to be equal to, let's say, WS over these all S. But so for example, that the Z of the WS is, let's say, small. Okay. So now, how small should this be? If I, for example, pick something which is like that. This is at this moment, for what we have proven, only we know that these kinds of G's contain the about IW fraction of the channels is only shown for this particular value, because we only show things that the I being away from the extremes is good. But if I use these ones, what is the block error probability here? Well, each of these channels which I'm trying to decode, I might make an error with probability delta. Okay, so if I'm conservative in my estimate, the error probability of the block error, I can only upper bound it by the union bound because I know nothing about the correlations between these error events. So this is going to be the number of channels that I'm using in this good set. This is like order n, okay, about the block length. It's some fraction of 2 to the I, okay, times this delta. Okay. But this number can be huge because even though delta is small, I need to multiply it by some things which is growing exponentially in the I. So this is like, so this G is like 2 to the I times the rate I want to communicate at. It's a constant. It is less than IW, but it's some number. Sorry? This is G, yes. I tried to script G because I want to reserve G for indices, script G for the channels, okay? 2 to the I times delta, okay? So even though this number is small, I multiply it by these 2 to the I, which might make it to be big, so I have no idea about what my error probability is. Okay? I need to show you something that I can replace this delta by something which is faster than exponentially small than the I. Okay? So I need to show that when the channels are good, these Zi, when it converges to 0, it does so faster than exponential in the I. Okay? It should go to, so this convergence to 0, when it happens, it should be happening faster than 1 over 2 to the I, so that even if I multiply it by this 2 to the I still get something which is 0. What we will show is that it does so, in fact, doubly exponentially in the I. What I'll show to you is that this Zi, when it goes to 0, as in just before noon, we argued that this Z should be about something to the power 2 to the I over 2. Okay? So this is, the I is appearing not at the exponent, but at the exponent of the exponent. So it's a very fast decay. Okay? So if we can show that, then all these concerns will disappear. Okay? Error propagation will be arrested because the Z's are really small, so the error probability is also very small. Okay. So that's the motivation for studying this Z and this diversion to these stochastic processes, etc. So I'm sort of jumping ahead and then coming behind. Okay, so I'm trying to give you the reason why I'm trying to do this bizarre computations here. Okay. So now that we have a clue that this Z is supposed to go to 0 doubly exponentially fast, instead of studying the Z itself, let me study the log of 1 over Z. Okay, so define Vi as being log of the 1 over Zi. So Zi is going to 0 means that the Vi is supposed to blow off to infinity. I want to show you that this is blowing to infinity fast. Okay. For example, exponential decay in the Z, in the I, would mean linear growth in the Vi. Okay. So if I was trying to show that the Zi was going to 0 exponentially fast, I would have to show you that the Vi is going to infinity linearly fast in the I. What we will show is that Vi is growing to infinity exponentially fast in the I, so that Zi is doubly exponentially fast going to 0. Okay. We will try to prove. Vi goes to infinity exponentially fast in I. Okay. All right. Good. So, and let's see how the Vi behaves. Okay. First of all, because we had these lemmas for the Z. Okay. So our lemmas for Z going to Z plus and Z minus. Okay. So the Z of W plus and Z of W minus with respect to these things, we'll say the following thing. So the Vi plus 1, okay, when Si is plus and Si is minus. Remember, S is the guy who's choosing the, do I go up or down at time I? Okay, so if Si is plus, you start from the V and then start channel W and you take the plus version of it. If you take a plus version, you have squared your Z, so you have double this logarithm. Okay, squaring the Z will simply multiply the logarithm by 2, so Vi becomes 2Vi. Okay, when Si is minus, you multiply Z by 2, okay, which subtracts 1 from the log. Okay, suppose this is log 2. Okay? Right. So multiplying the Z by 2 is same as subtracting 1 from the Vi. Okay? This becomes V goes to Vi minus 1. Okay? All right. So first I would like to give you a heuristic as to what is happening in such a process. Okay? So I guess I don't need to say any more, right? This picture is fairly clear. So for example, suppose we are in one of these paths which make the Z going to 0. Okay? We are on a path in which the V is blowing to infinity. We know for sure. Our only concern is that how fast. Okay? Suppose you come to a point in which, let's say, the V is, I don't know, 15. Okay? So suppose you are at some point in which you have a V which is, we start at point 15. Not a particularly big value, but I think it's good enough for our purposes to illustrate what's happening. And suppose that the next remaining, the following steps that we take with these S's are the following things. Maybe here, this is the V, okay, and the S. Suppose we do, I don't know, let's say a minus, I'm trying to guess a random sequence, okay, so let's flip things up, okay. Anybody coin to flip and then tell me minus and pluses? No, okay, just say some signs, not all minuses, okay, please, okay, so minus, minus, plus, minus, plus, plus, minus, minus, plus, okay, so, okay, something like this, okay. Let's see what happens to this V, okay. We encounter a minus, so we go down, okay. One more minus, we go down again, okay. We encounter a plus, this makes us 26, okay. We encounter a minus again, we make 25. A plus, we go to 50. Another plus, we get 100. Okay, a minus, 99. Another minus, 98. One more plus, 196. Another plus, 392. Okay. You see, I mean, in the fight against the pluses and the minuses, when the plus hits you, okay, you multiply by 2. Okay, and to sort of climb down from this 392 back to where you started from, will take you an extraordinary amount of luck to encounter a series of 3 and then something minuses to sort of bring you back to where you are. Okay, if you try to go down, 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 one more plus comes in. Okay, you're back to big again. Okay, so what you see is here, indeed, the plus signs. If you have somehow managed to get yourself to some place already close to 0, so if you are in this path which is supposed to getting close to 0 in the Z, sort of V is already something big. And even this number 15 was not, I mean, particularly stupendous number. It's a modest number on the way to infinity, after all, right? Even at here, the chance of digging yourself out from or maybe falling down from this height by the help of this minus signs is really a losing proposition. Okay? So consequently, to the first approximation, you can think of this V process as being similar to a different process, let's say V tilde, for which you ignore the minus sign this minus 1 to begin with. Okay, so it's not, of course, this is not correct. I'm giving myself too much in here. I'm saying that the minuses, they don't actually even reduce you. They do here, obviously. Okay, but if you believe in this one, then indeed, I mean, when you start from a V, you multiply yourself by 2 half the time. So a long sequence of going up to, let's say, n. You encounter yourself n over 2 of these multiplications by 2. So you'll be your V is going to grow exponentially at the rate half, okay? Because you're going to have half the time you're multiplying by 2. So you have v is going to be like 2 to the power n over 2. Vn is behaving like 2 to the power n over 2. So exponential growth in the of the v and the n. Okay, all right. This is not a proof because I need you to lower bound the v because I want to show you this thing. When I remove this thing, I'm upper bounding my v. So all we have shown is that v cannot grow more than exponentially fast. Okay, so this v, new process v, is an upper bound on the old process v because I removed that one. And the upper bound process is growing exponentially at a rate of 2 to the n over 2. That's an upper bound. But from this picture, we also see that it should not be too far off from the truth. Okay, so this upper bound should be reasonably tight. All right, let's now try to show that our intuition is not too far off. Any doubts at this moment? Because, I mean, I sort of gave a lot of information in this last 10 minutes.
What is that we know hold these parts.
Yes.
After a certain time, it will not hold beyond this.
Very good. Excellent. Yes. So you know that the v is never going to be below, let's say.
Say it's a fraction of this, and
Yes.
fraction is small enough.
Yeah.
And then we are multiplying by 2, so
Yeah.
these then will.
Very good. So let me actually write down what you said. The idea is the following. We know for sure, we know, since on the path where zi is going down to 0, vi is going to infinity. Fine. So on these paths, there exists, so on such a path, there is a, let's say, an n0, it's an n-time index, such that for all m bigger than this n0, let's say Vm is going to be bigger than, let's say, 100. Okay, it's a number that I just picked. Okay, so let's now take a look at this process from n0 onwards. Okay, what we'll see is the following thing. We will then see that this for these paths, the vi plus 1 is going to be equal to either 2vi or vi minus 1. That's the evolution. Okay. But the 2vi is vi plus vi. Okay. And the second vi that I'm adding, I know to be at least 100 because I know that from this point on, I never encounter any vi which is less than 100 is excluded. This is bigger than vi plus 100 or vi minus 1. Okay. So now let me actually make this number to be 101. Okay, as in Dalmatians. Okay, and the reason I took 101 is the following thing. So, and both of these things happen with equal probability, with 50% flips, boom, kind of like that. So what you see is that this is a random walk with a drift of 50. So average drift of this random walk is 50 up. So this vi on such a path has a drift of plus 50. So it's like a casino which is biased towards you. Okay, you have a chance of earning 50 rupees, okay, on the average each time you play. Okay. So the expect is then the following thing, that this vi should be growing like 50 times I in the long run. Okay, so we'd expect with high probability then if I put a number which is less than 50, for example, that if I make myself some conservative thing, if I ask what is the chance that the vi is more than 49i, that's a high probability event because the mean of the vi is around 50. The variance is not that much. It's in the order of square root of I because of the random walk here. So what we're going to have is that the vi is going to exceed 49i. Okay. So what we get for free from this argument is that the vi grows at least linearly. Okay.
So we can go exponentially also.
Uh-huh.
Vi minus 1 is, we can say that vi plus vi, that is 2 times vi.
Yes.
The second thing is vi minus 1. We can go it is 99 by 100 times vi.
So one time we are multiplying 99 by 100, other times we are dividing. So
Okay.
when we get log, so it's kind of sum.
Okay,
And
nice.
then if we take log of this again, then sum goes linearly. So this goes that way.
Very nice. Okay, all right. Let's do it actually your way, so that the proof will be a bit simpler. So the idea, let me rephrase this in the following way. You suggest that we keep this thing to be 2vi and replace the 1 by saying this is 2vi and this is minus 1 is larger than vi over 100. Back to this being 100. Okay, so since minus 1 is larger than minus vi over 100 because I know vi to be more than 100, this is to say that this is equal to either the I times either 2 or 0.99. Okay, and these are happening with probability half. Okay, so what you expect this vi to be after many steps. So if I look at for large I, we get v sub I should be about. So what you have is that you're multiplying by 2 I over 2 times. You're multiplying by 0.99 I over 2 times. These can all be made a bit more precise by saying it is I minus n0 blah blah so forth, but all these things are just constants. For large I, it disappears. So what we get here is that this is equal to the square root of 2 times 0.99 to the power I. Okay, all right. Or maybe I should write as being the following thing. Let me write as this thing as 2 to the 1/2 I, and I have to put here some small constant 1 minus epsilon. Choice of the epsilon has to do with getting the 0.99 to be correctly absorbed. Okay, so essentially I write 2 times 0.99 as being 2 to the power 1 minus epsilon. Okay, so this 1 minus is nothing but the log of 1 minus the logarithm plus logarithm 0.99. Okay, all right. And this epsilon we choose can be made as small as you want to by choosing this 100, which is an arbitrary number. Okay. Because the number I change here, if I make this into 1,000, then this n0 will get bigger, but who cares? Okay, but this number would have been 1 over 1,000. Okay, so we get here 0.999. So I can make this number as close to 1 as I want. Okay, all right. So what we conclude from here is that this vi is growing exponentially, and just at the rate that we discovered as the upper bound. Okay, so what we have shown is the following thing. At the end of the day, what we have is the following. So the conclusion is that if you look at the vi for any epsilon bigger than 0, the probability that of the following event, that the vi grows exponentially at least as fast to the I over 2 times 1 minus epsilon. This probability is the same as the probability that I goes to 0, okay? Because we only showed this thing on paths which are converging to 0. This is exactly equal to the I of w, okay? So this is the same as when zi goes to 0, the vi is growing exponentially fast, okay? All right. We also showed by the upper bound technique that if I do the same thing, that the chance of the vi grows exponentially at least as fast as 2 to the I over 2. If I put here 1 plus epsilon, I ask the vi to grow faster than that. Terribly sorry. This is I over 2, yes. At least as fast as 2 to the power I over 2, and 1 minus epsilon is at the exponent. Okay? And if I ask the same thing by asking, will the VI grow faster than 2 to the I over 2? This never happens. Okay. Because even the upper bound process, in which there was not a -1 sign at all, even that process was growing only like 2 to the I over 2. So V cannot grow faster than that one, because the other process, the process for which we didn't have this -1, this was only growing like 2 to the I over 2. So this doesn't happen. So in a sense, we have a fairly good idea as to how fast this VI process is growing when it is. Okay. Okay. Good. This is very nice for us, and thanks for actually simplifying my proof, because I would have bootstrapped from this one to show that blah blah. So this actually makes my life a bit easier. You say that's 15 minutes. Okay. So to all of us, so this adds to a few hours of time. Okay. So what we now have is that I could now say the following thing. If I now ask the following probability, the probability that the ZI is less than, so let's see, this, let me write like this. Log 1 over ZI, this was the VI. If I ask this probability of 1 minus epsilon, this as I gets large, okay, is equal to IW, okay, for any epsilon I want. To say this is it's a weaker statement than this one here. We said that this VI is growing like this. Right? And this one, if I translate to what a Z is, this is the same. Is the same as the following thing. This is the ZI being less than 2 to the minus 2 to the I times I over 2. Maybe it's better to write it like this, because when you put the slash sign, it's not so obvious where things come. Okay. It's like this. Okay. And I should also maybe note the following thing. 2 to the power I is the block length. So 2 to the I is, recall that the n is equal to 2 to the I is the number of channels that you are using to communicate. So this is also equivalent to the Z of these WS's, okay, being less than 2 to the minus n to the power 1 minus epsilon over 2. Essentially, for small epsilon, this is the same as the square root of the block length. Okay. So this probability is now saying the following thing. So if I count the number of channels at level I, namely after I polarization steps, for which the Z of these channels is less than 2 to the minus n to the 1 minus epsilon over 2, essentially square root of n. Okay. And if I divide this thing by the total number of channels, okay, this is getting close to IW as I gets large. Okay. So this is very nice for the following reason. Now, you give me some rate which is less than IW. You say, please find me a whole bunch of channels, R times n channels out of the n synthesized channels that you had. I can ensure that as long as R is less than IW, I'm going to find channels whose Z is less than that. Okay, all of them as less than that. So the total error probability is the number of channels I picked, which is at most n, okay, upper bound that, times the Z. Z is the upper bound on error probability. I have n times something which is exponentially small square root of n. So that number is also going to 0. Okay? So if you multiply with something exponentially small, a polynomial factor at the n, okay, makes no difference. You still go to 0. Okay? Consequently, this is sufficient to show the following statement. So given a rate which is less than IW, okay, as n gets large, or I gets large, we can find r times n is equal to r times 2 to the I, n is equal to 2 to the I, channels, synthetic channels, among n synthetic channels. After I polarization steps, each of such that each of the Rn channels has the Bhattacharya parameter, which is less than 2 to the minus, okay, let me start with given epsilon bigger than 0 and r less than IW, n times epsilon over 2. Okay, so fine. So this is from there. Okay. Consequently, if those channels are used for communication, so consequently a polar code that communicates data on these, let me call them good channels, okay? And sends frozen bits over the other channels which you don't use, remaining n times 1 minus r channels. Has a block error probability which is upper bounded by the number of channels that you picked and the largest of the z parameters. Okay. Over 2. Okay. So what you see is that this number can be made as small as you desire by picking I big enough. Okay. If I is large, n is large. If n is large, n times 2 to the square root of n goes to 0. Okay. So this number, it goes to 0 as I gets large. Okay. So this one says that you can create codes, reliable communication codes, through this construction at any rate which is less than IW. Okay. So you give me any rate which is less than the symmetric capacity of the underlying channel. We can construct polar codes which I goes to I gets large. This arrow sign means maybe let me put it like this so that it's clear as to where I is going to. As I gets large, this upper bound on the error probability goes to 0. So you can find as good codes as you desire. Okay? And the bound is on the block error probability and so forth.